Okay, lovely. So thank you everyone for coming along and joining us tonight. It's lovely to see you all. And as I say, after we've had the presentation from Roy, I'll open it up for questions. Also, we can have just a bit of a chat together because we don't get to see each other very often, and it's nice to meet up and see everyone. But Roy Stewart has agreed to do this evening's talk, which is great. And it's going to be on exoplanets 5,000 plus and counting. So this is an intriguing subject and I'm thoroughly looking forward to it. So over to you, Roy, and thank you.
Right, thank you for the invite. I know it's probably a bit unusual for a talk on astronomy in this group, but astronomy is probably the oldest of all the natural sciences. And ever since we were able to sort of look up and start thinking, we've contemplated what's happening out there. And it's a huge story, but what I'm going to try and concentrate on tonight is a story of exoplanets. And this is probably one of the most research orientated subjects at the moment. There's a great deal of time and money being spent on it, and hopefully I'll show you some of the results and why. So if I can sort of work through the slides, hopefully. Right, there are many complicated definitions of exoplanets, but this is the simplest one. And this is one from NASA. And it's an exoplanet is any planet beyond our solar system. Most of them orbit other stars, but we do realize now there are free floating exoplanets, and these are called rogue planets, and they orbit the galactic center and are untethered to any star. In the old days, an early name for an exoplanet was an extrasolar planet, and you may still see this being used in some areas, but we tend to an exoplanet now. The idea of exoplanets is not new. Epicurus, in a letter to Herodotus around about 300 BC, quoted, "There are an infinite number of worlds, some like this world and others unlike it." So people have been thinking about the possibility of other worlds in the universe for a long time. But it's only with the advent of recent technology that this has really developed. A little bit of history. The first detection occurred in 1992. This was found in an unexpected environment. It was orbiting a pulsar. Now, pulsars are particularly violent phenomenon, and they give out massive doses of radiation. And they found 3 exoplanets. And the reason they found them was that they were very large planets, so they were fairly easy to detect. You can still find the odd planet round a pulsar, but people are not concentrating on this area anymore. And we're just mainly concentrating on what we would call normal or main sequence stars. I'll explain a little bit more about that later on. But the first real evidence of a planet around what we call a normal star was 51 Pegasi. Now, in the nomenclature of exoplanets, the star is just called 51 Pegasi or 51 Pegasi A, and the first planet discovered that circulating a star is always given the name B, and the following planets are then C, D, etc. The planet 51 Pegasi B was around half the mass of Jupiter and orbits around its parent star in just over 4 Earth days. So that's a phenomenally quick rotation for a planet half the mass of Jupiter. And it lies about 8 to the sun, the Mercury. I'll be talking a bit later more about these, what we call Jupiter-like or hot Jupiter planets. But the Jupiter-type planets were the first ones to be discovered. The 2 astrophysicists who discovered it were awarded the Nobel Prize in 2019 for this discovery, for this first confirmed exostellar or exoplanet orbiting a sun-like star. And they're there standing outside the observatory in Chile. Now, Since 1995, this area has taken off and it's become a very dynamic research field. And the latest quote I can find for the number of confirmed planets is as of 12th of July 2023. And there's 5,470 confirmed at the moment in 4,069 planetary systems, with 900 systems having more than one planet. Now, it's interesting, if anybody's read the article in Countryside, when I first wrote this article, the numbers at the 1st of February 2023 were just over 5,300 confirmed exoplanets. So you can see there, in the basis of 4 or 5 months, it's already gone up by a considerable amount. So that just illustrates that this is a continuing area of discovery and research. Now, nobody knows the true numbers of these exoplanets, but you can make an assumption. And assuming there's 200 to 250 billion stars just in our Milky Way, it's estimated that there could be 11 billion potentially habitable Earth-sized planets in the Milky Way. Now, this will rise to 40 billion if you consider planets orbiting the numerous red dwarfs. And I'll explain a bit more about what we mean by red dwarfs and the problems that they can cause when looking at exoplanets. But that number is just in our Milky Way. So if you're now thinking of the universe as a whole, you're looking at trillions and trillions, because they now think, and they're reasonable in this estimation, that every star possibly has planets associated with it. Now, the missions are either dedicated to exoplanets or look for them as a sideshow. And the first one that really looked at them in detail, but not as its main topic, was Hubble. And if you look at the bottom of this picture, you can see the ones that are there basically looking at exoplanets as a sideshow. They're not dedicated to it. But having said that, the Webb telescope is now spending a lot of its time looking at exoplanets. And the telescopes at the top orbiting in space are all dedicated to exoplanet missions. And you can see already there's a few due to be launched, dedicated purely to looking at exoplanets. So as I said, this area of discovery and research is just going to keep going and going and going. Now, the trouble is, the old proverb, looking for a needle in a haystack, does work in this system, because planets emit little or no light of their own, and they rely on the host star reflection. And the host stars tend to shine much brightly than the planets. And the analogy that's often used, it's like trying to see the light from a dim candle in front of a raging forest fire. It's that difficult. Currently, there's 6 tools that are used to spot hidden planets. There's what we call direct and indirect detection. Direct detection is direct imaging, and indirect, we have radial velocity tracking, astrometry, transit, pulsar timer, and gravitational microlensing. As I said before, pulsar timing, we're not really looking at that in great detail at the moment. And gravitational microlensing tends to rely on one-off events. So these last 2 will not be discussed, as they are not really proved, even though they can be used. So the hardest way to detect an exoplanet is due to the extreme contrast between the light emitted. So rather than using, we tend to use infrared radiation. And the visible output from a planet like Jupiter is just 1 billionth of that of its host star. While if you look in the infrared, it drops down just to a factor of a few thousandths. So that's why a lot of these telescopes tend to operate in the infrared range, especially the James Webb, which has near, middle and far infrared cameras. Another method to physically try and block out the starlight is to use the principle of what happens in an eclipse of the sun. So you can put a disk that covers the bright central core of the star, hopefully just leaving the corona and the outer region. And in that aspect, you try and pick up the star in the dark, in the exoplanet against the star's darkness, if possible. And this was used on a very large telescope, and this obtained the first image of an exoplanet. Now, there are future imaging missions which will try and directly observe planets that have been detected mainly by the radial velocity technique. And what these techniques like radial velocity and transits do, they can identify the presence of a planet, and then you can concentrate the search by using mainly optical instruments to try and do direct imaging. So you can use these other techniques as a sort of preliminary process. But this is a picture, and it's the first one of an exoplanet orbiting a brown dwarf. And it was imaged by the Very Large Telescope in 2004. But the actual identity and characteristics of the planet were not confirmed until after about 1 year of observations, which happened in 2005. Now, the planet, which is 2M1207b, again, B is the first planet, is 5 times more massive than Jupiter. And this is one reason why it was easy to see by direct imaging, because of its huge size. And it orbits the brown dwarf at a distance 55 times larger than the Earth to the Sun. So it's nearly twice as far as Neptune is from the Sun. So that's a big distance. But as I said, because of the huge size of the exoplanet, it was able to be imaged directly. And this image lies at a distance of 230 light years away in the constellation of Hydra. The image is actually based on 3 images in the infrared range. Now, in November 2008, there was a group of astronomers at Keck telescopes announced the imaging of actually 4 planets orbiting a star, HR 8799. Now, again, these were operating in the infrared range. This star that is a young star, so it's still in the very early stages of its formation. But by looking at infrared, you can look at the heat from these planets, the residual heat from the planets as they're forming. And with repeat observations over time, they actually were managed to produce a video image of this. And if you're interested, if you go down to YouTube and do a search for this, you can actually see these planets moving relative to the star. As of April 2050, 50 exoplanets have been discovered by this process of direct imaging. Now, radial velocity. This was one of the early techniques to detect planets. Now, what most people don't realize is that the star not only rotates, but it can actually move in a very small orbit by itself, and it feels the tug of the planets or planets on it. So not only do the planets feel the tug of the star, the star itself can feel a slight tug on the planets. It's only minute, but we can detect it. And what we tend to do is we look at the velocity of the star along the side of the observer. And that's what we're looking for, is you're looking at changes in radial velocity as the star moves, its spectrum shifts towards the red end or the blue end. So it depends on whether the planet is moving away from our line of sight or to our line of sight. And this is known as the Doppler effect. You've probably come across this before when discussing sound, when you hear the sound of a siren that goes past. When as the siren's approaching you, it gets shifted to the blue end or the higher frequency. So you hear it as a higher note, and when it's going away, you hear it as a lower note. And it's the same with light. When light is moving away from us, it gets red shifted, and when it's moving towards us, it's blue shifted. Now, you have to rely on the fact that you're looking directly in the line of sight between the planet and the star system. And there is a system at the moment called HARPS, which stands for High Accuracy Radio Velocity for Planetary Researcher, which is based on an Earth-mounted telescope in Chile. So this is not a space telescope, this is a ground-based one. And this is just a cartoon showing you that if this is the planet and this is the star, obviously they are having a slight effect on that. The star will tug more on the planet, but the planet will have this minor tug on the star. And when this is coming towards us, the light, when the planet is going away, you get red shifted, okay? But when the star is coming towards us, it gets blue shifted. So we can tell the difference between the spectral lines. And if you look at the spectral lines, it's only minute, but you can see that they actually shift slightly. Yeah, so they move towards the red as the star travels away to us, and they move back into the blue as the star travels towards us. And that's based purely on the slight gravitational effect that the exoplanet has on the star. Now, most of the planets so far have been discovered by this method are very large and very close to their stars. So because they're very large, they have a more impact on the gravitational tug. So the change in redshift and blue shift is quite noticeable. Now, most of these planets are called super Jupiters, and they're much larger than our Jupiter. Sometimes they can be extremely large, almost to the size of small suns, and they orbit the stars in a matter of days. And the beauty of this is because they orbit in days rather than many, many tens of years, you can take repeated measurements. And because you can take repeated measurements, they then become more positive. And as I said, because of this, because of their size, they tend to cause a large wobble on the star, and we can see these a bit more easier. As of November 2022, over 1,000 planets have been discovered by this technique. Now, the other term that we use is astrometry. And basically, this means you can precisely measure the movement of a position and movement of a star. Until recently, we didn't have the telescopes to resolution to detect this type of motion. But astrometry will be more sensitive to planets with large orbits, which is an advantage over the other methods. Only 4 exoplanets have been detected using this method so far, but they have been confirmed by other methods. But there was a mission launched in 2013 called the Gaia mission, and this is still active. Now, Gaia's mission originally was to track stars, nothing else, just to track stars. And its initial aim was to create a database of over 1 billion astronomical objects, okay, including anything in the Milky Way, from quasars to asteroids. Now, the thing is, it's already exceeded any expectations of it already. So its original aim was 1 billion, and currently it's up to 1.8 billion stars alone. That's without any other objects at all. Now, because it's measuring stars precisely over repeated periods, it's expected that it will detect minute adjustments in the star. And by finding those minute adjustments, you can then aim other telescopes at exactly that star position and see more precisely if there is an exoplanet moving around that star. And it's expected that Gaia will detect up to tens of thousands of exoplanets out to around 1,600 light years. Now, This is the Gaia data. This was the latest release, 3. And you can see 1,811,709,771 star positions. So those are very, very precise positions. And it will measure those again and again and again, and just see if there is minute changes in those star positions. Well, that's the Gaia data at the moment. And this is the Gaia sky map. Now, this looks quite unremarkable, but this is a large scale map looking into the center of our Milky Way. So the center is there. That's where the supermassive black hole is at the moment. These are the small and large Magellanic Clouds. But that picture is made up of 1.8 billion stars with a precise location known for every single one. So this is what astrometry involves. It measures the star very precisely over time. And if you can see any change in the position over a sky over time, and you get this sort of what we call precision movement, then if it's doing that, it's a good indication that there is an exoplanet surrounding that star. And as I said before, then you can go and do other techniques and look more precisely at the characteristics of that exoplanet. Now, the next method is transits. And most people who've done astronomy will be familiar with transits because people go to great lengths to look at transits of planets across our sun, particularly Mercury and Venus. Now, any planet that crosses in front of a star is called a transit. And when it crosses, you get a little bit of dimming detected at regular intervals every time it crosses the star. So if these dimming occur at regular intervals and at a fixed repeated length of time, then it's highly likely that the dimmer object is a planet, exoplanet orbiting the star. Some of these objects might be small dim stars, and they might be in what's called a binary system, but most of them will be exoplanets. Now, transit photometry is currently the most effective and sensitive method for detecting exoplanets. It's particularly advantageous for space-based observatories as it can stare at stars for weeks or months. It can be performed with ground and quite small telescopes, but if you've got one based in space, dedicated just to looking at these minute movements and dimming effects, you can train a telescope literally on one area of the sky for years at a time. Oops, sorry. Now, how much the dimming occurs relates directly to the size of the star and the planet. Now, a small planet transiting a large star will only create a slight dimming, but if there's a large planet present, then the dimming will be quite noticeable, and you'll be able to pick that up a lot more easier. The size of the host star can be known with quite considerable accuracy because you can measure its spectrum, and from its spectrum, it gives you an idea of the class of the star and its size. And with the dimming effect of the planet, it gives you a good estimate of the planet's diameter, but not its mass. Radial velocity tends to give you an indication of the mass, but not its size. But transits give an idea of its size, but not its mass. Now, if you combine the two together, you can calculate what's known as density. And it's density that can give you an idea of whether the planet is, say, rocky, gassy, or somewhere in between. Okay. And this is just a diagram taking you, showing you density plots. You don't have to worry too much about the complexity of this, but you can see roughly, you can break it down into iron containing planets, silicate containing planets, ice giants, and the Jupiter, Saturn type planets. And if you can see here, there's a picture of Saturn and Jupiter lying in these class of planets. You've got Uranus and Neptune in here. Then you've got Earth, Venus and Mars in here, and then Mercury in here. So density can give you a rough idea of the composition of the exoplanet. Now, for a transit to occur, you've got to be almost looking exactly edge on to the observer. Obviously, transits will occur all the while, but if you're not in exactly the line of plane looking at that, the planet circulating directly in front of its companion star, then you're not going to really detect a true dimming effect. Now, also, the dimming can only last for a tiny fraction of its orbital period. Now, a planet might take months or years to complete its orbit, but the transit will only last a few hours or even a few days. So what astronomers like to do is concentrate on possible exoplanets that are transiting, or their orbits are in days, months, or perhaps only a year, because then you can take repeated measurements over time. Okay. So the transit photometry method is heavily biased, obviously, towards these planets that have short period orbits or close to the stars. Now, this is actually data from the James Webb Space Telescope. And you can see here, this is just picking up the background starlight. And as soon as a planet moves in front of that star, it will block out a little bit of light. And then once the planet is transited, you get back to the starlight. So judging by the width and the depth of that transit, that curve there can give you an idea on the size of the exoplanet. Now, that's what we call the primary transit. What the beauty of these new telescopes, especially James Webb, can do is it can also pick up what's secondary transit. And that occurs when the planet goes completely behind the star. So what you're looking at is the spectroscopy from the star itself, and then you deduct the star's light when the planet is in front of that spectrum. And then by looking at the difference between the two, you can determine the planet's actual spectrum itself. And by looking at the spectrum and looking at that spectroscopic information, it can give you a clue to its temperature and also a hint to the composition of the atmosphere. And of course, one thing that interests people who are looking at exoplanets is the evidence of what we call biosignatures, because biosignatures can indicate possible evidence of life. So that's one of the holy grails of exoplanet research, is to try and pick up a biosignature. And this again is from a hot gas giant, WASP 39b, picked up by the James Webb, and it's looking across the wavelength of light across quite a few different wavelengths, all the way from north up to about 6 microns. And if you look at the amount of light blocked and then look at spectroscopy, from the peaks in these different wavelengths can give you an indication of either the compound or the element present. And if you notice, some elements, carbon dioxide, carbon monoxide, water, have emissions at different wavelengths. This is quite common. So this is how you can give a specific identity to a compound. And this one actually shows the presence of sulfur dioxide, carbon monoxide, carbon dioxide, and water, which is properly typical for a gas giant anyway. But at the moment, there's no evidence of a biosignature there, such as oxygen. But you can see how sensitive these measurements are identifying molecules in planets light years away, millions and millions of kilometers. Now, what we need to talk about is the Kepler. This was one of the first telescopes put into space specifically to look for exoplanets. And what it did was it looked at one field of view, nothing else. It just concentrated on one particular small field of view in the area of Cygnus. And it did that from March 2009 to November 2018. Now, what Kepler found is, and what we've suspected, but we didn't know till the data started coming in, is that planets actually outnumber stars. And this shows that possibly every single star system in the universe has some kind of primitive solar system circulating around it. And what Kepler did was, not only did it show Jupiter type planets, the large ones, it also showed that the galaxy is teeming with terrestrial sized worlds. And it concluded that 20 to 50% of stars are likely to have four small possible rocky type planets. And not only did Kepler show that there were terrestrial planets and Jupiters, but it also discovered another two types of planets as well. And the most common one it found was the size of a planet that fits somewhere between the size of Earth and Neptune. Now, these planets do not exist in our solar system, but they're very common in other solar systems around remote stars. Some people refer to them as little Neptunes. Some people call them large Earths. And it's a bit of an unfortunate term when they talk about large Earths or super Earths, because strictly speaking, they are not really Earth-like in nature. But when people get excited, they call them super Earths, then people immediately think, oh, we found a companion Earth in somewhere in the universe that is a mirror image of ours. But unfortunately, that hasn't turned out to be true. Now, while our own solar system has four terrestrial type rocky planets, Kepler found systems with considerably more planets, up to 8. But usually these planets orbit very, very close to their parent stars. And they tend to be referred as compact systems. And most of them, you can have 8 planets orbiting within the orbit of the Sun to Mercury. So if you looked at our solar system as a comparison, we could put an extra 7 planets between Mercury and the Sun. So it begs the question, how are these solar systems formed? I'll come to this at the end, okay? But the Kepler data, the Kepler mission ended in 2019, but the data is still being analysed. So there are far more planets that are likely to be identified from the Kepler data over the next 10 years, easily. And this just shows you the data from Kepler to, from pre-Kepler, to Kepler. And you can see here, pre-Kepler, most planets were hot Jupiters, large Jupiters, and a few Neptune type ones. But look what Kepler found. Most of the planets it discovered sat in this range between Earth and Neptune. So these cover anything from a terrestrial to a small icy world. Currently, we think there's 4 types of exoplanets. There's the gas giants, what most people call hot Jupiters or big Jupiters. They can be hotter than some stars, and I'll talk a little bit about that in a bit. 30% of those planets found are giants. Only 4% are small planets, terrestrial. 35% are Neptune-like, the ice giants, and 31% are what we call these super Earths. So anywhere between something slightly bigger than the Earth and Neptune. And as I said, these do not exist in our solar system, but they are common in other solar systems. Why? We don't know. So hot Jupiters. They were the first planet discovered because they're very big. 1% of all planetary systems so far have hot Jupiters. And when we say a hot Jupiter, they range in size from about a third of the size of our Jupiter up to about 10 Jupiter masses. But the interesting thing is these Jupiters orbit their host stars very, very close range, usually much closer than the orbit of Mercury. So a year on a typical hot Jupiter lasts from hours to a few days. Now, Mercury takes almost 3 months to complete a trip around the sun. So it's quite bizarre that you've got these massive lumps of gas being thrown round the star in a few days. It's just unbelievable, and nobody's quite worked out yet why. And because most of them are so close to the sun, they're what's known as tidally locked, and this is equivalent to our moon being tidally locked to the Earth, and one face is perpetually always facing the star. So in these hot Jupiters, they could have fantastic temperature changes. Okay, so it could be extremely hot on one side and extremely cold on the other. Now, the surface of a typical hot Jupiter can get as hot as almost 5,000 degrees, and cooler ones only get to about 1,400, but that's still hot enough to melt aluminium. And again, as in most science, discoveries raise more questions than answers. Now, how do these hot Jupiters form? They think there's two ways they can do this. One is actually in situ formation from the protoplanetary disk, or the other one is by migration. Now, most people assume that our solar system has been the way it is forever and ever. We now know in its early formation, Jupiter towards the sun and then back. I'll show you a little chart about this in there. Along with Saturn is known as the Grand Track hypothesis. But most hot Jupiters discovered in extrasolar systems could have just migrated inwards and stayed there because there was no outward backwards pull from a Saturn type planet like we've got in our solar system. It's also been shown that they can form in situ, and there's no reason why they can't do that. And it's been put forward a model that some of those super Earths, because they are slightly larger than our Earth, could attract large amounts of gas onto their surface. And because they could pull in large amounts of hydrogen and helium, they could then go on to form gas giants. Now, obviously, the next question is, how do these gas giants survive so close to the sun? And everybody thinks surely all that gas should be just completely blown off or evaporated. Now, we have seen that some less massive Jupiters have been found to have some of their atmosphere being blown away. But if you get a large Jupiter, so incredibly massive, it's been proven that over the lifetime of its parent star, only 1% of the mass of Jupiter will be lost to photoevaporation. So it looks like there could be two possible ways to form Jupiters. This is the Grand Track hypothesis for our solar system. So in year naught, Jupiter, Saturn, and some of the gas giants form. Rocky asteroids and our inner planets haven't formed yet, but they reckon from about 70,000 years after the formation of the solar system, Jupiter actually migrating towards the sun. Then Saturn migrates in towards it. And if you notice, it creates this huge disturbance of all these asteroids. And if you look at the moon is peppered with craters. And that's something that's evident from what we call the Great Bombardment. Now, Earth would have suffered the same fate, but because the Earth is geologically active, all that evidence would have been eroded away. But because there's no geological activity on the moon, or very little, you can see evidence of that Great Bombardment. Now, 300,000 years after the formation, Jupiter starts to move backwards, and we think it's moved backwards because Saturn moved out first and it's being pulled, it's pulling Jupiter back. And at the same time as it's pulling it back, it moves Neptune out into its extreme orbit as well. And about 500,000 years after the end of the movement, it starts to roughly starts to settle down into its current formation. And then you get the rocky asteroids starting to coalesce together to form the terrestrial planets that we know as Mercury, Venus, Earth, and Mars. And this is the current state of affairs. And it's thanks to Jupiter now being in its current position that it keeps control of the asteroids in a system between Jupiter itself and Mars. And if that system wasn't in place, we would be continually bombarded by asteroids, and we'd have more than one Jurassic Park event. Now, one of the most well-studied systems, exoplanet systems, is about 40 light years from Earth, and it's called the TRAPPIST system. And if you look, it's got 7 planets, and they're all roughly, 3 of them are roughly the same size as Earth, and some are smaller. But these are all rocky type planets. But if you look to the distance to the star, 0.6 of an astronomical unit. Now, 1 astronomical unit is the distance from Earth to the Sun, and Mercury is 0.3. So these 7 planets all orbit within the range inside what would be our Mercury. So they're all very, very close to the Sun. So all these 7 planets rotate very, very quickly. They're all rocky, and they're all very close to the Sun. So the chances of these rocky worlds harboring life is, I'd say, non-existent. Now, when we talk about exoplanets, we need to mention a little bit about the stars themselves. Now, most stars lie on what's called the main sequence, which is this line of stars here. And if you look, our Sun is there. It's what's called a G2 type star. As far as I know, we've never found another type G2 star in the solar system. We found plenty of G stars, but not a specific G2 type stars. Most of the stars that we've found are red in character and are M class, and these are red dwarfs. We get supergiants like Betelgeuse. Betelgeuse is interesting at the moment because it's swelling and contracting, and nobody really knows what's going on, but it could actually go supernova pretty soon, we think. So most stars line the main sequence. These are short-lived. These blue stars are very short-lived and very, very hot. These are extremely long-lived and dim. And this one, the G-type stars, are perfect for establishing life. Now, you might think these would be better for life formation because they're long-lived, but I'll explain a little bit more about that in a moment. So that's the star sequence, and we're there. And most planets so far have been discovered around red dwarfs. Now, the reason I talk about stars is because the star's environment will have an effect on where planets could possibly harbour life. And it's sometimes referred to as a circumstellar habitable zone. You probably know it better as the Goldilocks zone. You've probably heard that term in popular science. And it's this green area which forms the Goldilocks zone. And you can see our G2 type star there, roughly about 5,500 degrees Kelvin. We sit exactly in the middle of the Goldilocks zone. Venus is too much in the hot zone, and Mars is creeping towards the cold zone. But if you see, the hotter a star, the farther away the habitable zone is. And if you look at red dwarfs down here, you can see how close the zone, the Goldilocks zone, has to be to the star. Now, you might think, well, it's a Goldilocks zone. That's fine. The trouble is, these red dwarfs, even though they're long-lived, are just for comparison, our star is halfway through its life cycle. Yeah, it's about 4.5 billion years old. So it's probably got another 4.5–5 billion years to go. Red dwarfs, it's estimated, can live for tens of billions or even trillions of years. So they are extremely long-lived. So the possibility is life has got a huge chance of arriving and evolving over time. The trouble is, even though they're small, they're not very nice type of stars. They give off flares, massive coronal ejections, lots of radiation. They can suddenly explode. So if any life did start to form, it could almost be totally eradicated in the blink of an eye. Okay. Now, there's Kepler's, yeah, compared to M stars. So you can see one of the interesting ones at the moment that has caused great interest is Kepler 452b. These are, they're interesting because they've been detected, but this is the most interesting one, Kepler 425b. It circles 452 star. It's a G-type main sequence star located 1,800 light years away. Now, it's similar in temperature to our sun, but it's 20% brighter, 30% more massive, and 11% larger. And it's about 6 billion years old, and it possesses what we call high metallicity. Now, because it's not exactly the same as ours, it can be considered more as a solar analog than a solar twin. But the interesting thing is, if you look at the size of Earth to Kepler 452b, there is a difference. Now, at the moment, we only know one planet orbiting this star, and that's Kepler 452b. Now, it orbits at a distance very, very similar to our own Earth, 1.4 astronomical units. So it's only just slightly further out. And the orbital period is very similar to ours, slightly longer. The only problem is the mass is 5 times that of Earth. It's bigger, and therefore pushing it into the super Earth category. Now, it's probably still a rocky planet. It may have geological activity. It might even have a Goldilocks zone, but it's receiving more radiation from its sun. It's got more gravitation, and it's got more mass. And it's highly likely, therefore, to have developed a runaway greenhouse effect. So it's possibly in the state that we might be in a few years' time, given our current climate. Now, stars can not only rotate around one star, they can rotate around a couple of stars in what's called a binary system. Binary systems are where one star revolves around another. And as of July 2019, we found 97 planetary systems with 143 planets around binary stars. Now, these planets, they can just orbit one of the stars in the binary system, that's called an S-type, or they can orbit both stars in a P-type system. Most of the ones we found at the moment are S-types. Okay, there is a third option, but at the moment this is only theoretical. It can exist, but no planets so far have been discovered in this area. Planets in this T-type orbit are sometimes called Trojans. Diagram, there you go. There's the two stars. So the stars will actually move around each other. So the planet can actually move around one of the stars, or the planet can move around both of the stars. It's possible. And this is the T-type planet, where the planets are in the same orbit as the lower mass star, and they're always 60 degrees before it or 60 degrees after it in what we call Lagrange points. Now, this paper was only published in February of this year, and this is the first one that's tried to take all the evidence together to try to explain the formation of these extra solar system, exoplanet systems. There's the reference if you want it. If anybody wants to email if they are interested, it's a 2-part paper. It's fascinating. It's very scientific, but this is the take-home message. There seems to be 4 planetary systems in the universe. There's what we call ordered. So if they go, so this is the star, and this is increasing distance from the star. So if they're ordered, they go from a smaller size to a larger size. If they're similar, which is the TRAPPIST system, this is sometimes referred to as a penapod system. There's anti-ordered, so they go large to small. So these would be these very hot Jupiters close to the star with smaller planets here. Or we've got the mixed system. Now the mixed system is ours. Now, as it stands, we've never found another mixed system. Every planetary system we've found around the star at the moment is either similar, anti-ordered, or ordered. We haven't actually found a mixed system. They've provided a mathematical model based on observational data and synthetic catalogue data. And what they've said is what system you end up with depends on the mass at the start, the gas disk. So if it's less than 0.03 solar masses or greater than 0.03 solar masses, it depends on its metallicity. So if its iron to hydrogen is less than 0 or greater than 0, the solids, if they are less than 1 mass of Jupiter or greater than 1 mass of Jupiter. So you can use these combinations and trace. Now the nodes are the thickness of the nodes are the probabilities that they are the important points in forming these systems. And for a combination of all these will give you the one. So our one ordered depends to a large extent on the solid disk and metallicity and a relatively large gas disk. It's a fascinating paper, but if anybody wants to, I can get them for them. So as I said before, we found all 3 apart from this mixed one. And this new mixed one is unique to us. And the conclusion is, it seems that our solar system at the moment is unique and we are the odd one out at the moment. So it looks like we might be just the result of a unique series of events, accidents, flukes, call it what you want. But at the moment, it looks like that's it. And thank you very much for listening.
Unmute. There, I've unmuted. Roy, what an amazing talk.